Good morning. Today we are gonna start doing some examples for chapter 7. Remember last time we had the lecture about the linear algebraic equations, and we talked about all the possibilities of solution or unlimited solutions or unique solutions, and talked a bit about the ranks and how we found out if there is a solution, or if there is no solution, or if there is unlimited solution. We talked also about the RREF command, so we talked all about the possibilities of solving linear algebraic equations. So today we want to start doing some problems, and I'm hoping that you guys are doing also all the problems that I am doing. It's kind of practice for you. It'll be easier when you're doing your homework or your exam, and I'm hoping also you are keeping track of all your exams that's been assigned on Canvas, all your homework assignments, and also you have a midterm exam and you have also a final exam. We'll talk about this later on as well. But please follow up with Canvas, all the announcements, and also all the assigned homework and others. So yeah, let's work some problems. Share the screen here. And so this is already again uploaded on your on Canvas, so you can pull it up out and then start working on this yourself. So use MATLAB to solve the following problems. So these are sets of equations. So we're going to start with A, B, and C, and we'll see what we get. So let's yeah, let's scroll this one here and open MATLAB. All right, so we're gonna start with really don't have to do any. I mean, in your case, if you're doing this as a homework, you definitely have to do a script file. But in our case here, I'm just gonna do it without a script file. So let me just because it's just a couple of lines here. So let's do it in the command window. All right, so let's start with the first part. So you have A, in this case, is equal to, let's open a bracket. You have -2, 1, semicolon, and the second equation is -2 and 1. Now, just looking at this, before even we solve it, we know that this one is going to have no solution. And just the reason why, if you look at this one, is just like an equation of line, and the slope is -2. So these two lines are parallel to each other, so they will never intersect. You never have a unique solution. So, if you were to B, then this to B is, or just to X, here is -5 and 3. So X is equal to A, and then we're going to do the left division B. Right? So let's see what we get. We get X infinity, infinity, which means that there's no solution, and it says matrix is singular. Right? When we talk about matrix is singular, that usually there is no solution. And if you just do the if you do the determinant of A, which is -2 times 1 minus -2 times 1, that will give you a 0. When the determinant of A is 0, definitely there is no solution. So yeah, let's talk about yeah, let's do the B. So B also we're gonna do A equal -2 1. You know, this A is this coefficient of X and coefficient of Y. This is how I'm getting those. So for the second equation is -8 and 4, close the bracket, and I can also do let me do B is equal in this case 3 and 12. Okay, so even with this one you're probably gonna get the same thing, because if you notice, I mean, before I do any calculation, if you notice that's if you multiply the first equation by 4, you're gonna get the second equation. So so it is actually one equation and one line, right? Just multiply it by 4, you will get the same equation. So if you do the division, so and you will get the same thing, not a number in this case, because matrix is singular. So there is a slight difference in there, because when we say it's also not a number in this case, because also this is the same equation, and it's not like two equations or two lines that this is exactly the same line. So there's no way it's going to intersect with anything because it is the same line. So also it's a singular. So let's do the third one. So the third one is also A. Let's see what we get. -2, 1, -2, 1. And also, again, these are going to be parallel lines. So you can tell now by looking at the equation, you will see that you have a no solutions in there, and -5.0001. Again, we'll do X oh, see, I made a mistake here. So we'll put a column instead of a semicolon. So and do all right. Again, it's infinity, infinity. The matrix is singular, and you can tell that the slope is the same for both lines. It will never intersect. So let's do this one here, D. So solutions. So let's do D and see what we have. So A equal, open bracket, 1, 5 minus 1, and 6. Right? And then semicolon, 2 minus 1, 1 minus 2, semicolon, third row, then -1, 4 minus 1, and 3 semicolon, and then the last equation 3 minus 7 minus 2 and 1, and close. B is equal, open bracket, 19, first row, 7, second row, 30, 30, row, and minus 7, 5. Right, close, semicolon, and we're going to do division to see what we get. So if you look at this, you get x1, x2, x3. So there's a solution. So if you, for any reason, if you want to know if this is a unique solution and it is not a least square solution, so you can just do the product and find out what B is. So if you do, for example, A times X, for example, you will get 19, 7, 30 minus 75, same as B. So which means that this is a unique solution, is correct. All right, so we've done so far no solution and unique solutions. So let's solve this problem here. Let's talk about this problem. This is a circuits problem. So this is the circuits. Let me just enlarge this a little bit. So you'll see that the circuit has there's actually 4 individual circuits, actually 3 individual circuits. And if you do the voltage or the Kirchhoff's voltage law, if you apply it in each loop, you will get this equation here, these 3 equations, right? We know how to do this. So again, this voltage plus this voltage drop plus this voltage drop should be equal to 0. Same here, right? So we do, that's what we learn how to do. And so we do, you can start this way, it doesn't matter, or this way, and then solve for these 3 equations. Right? So these equations, we try to find, we have the resistance, but we don't have the current. So we're trying to find these currents in there. And but just remember that there's how many currents you have. If I enlarge this a little bit, enlarge it one more. So you have I1, you have I2, you have I3, I4, again I3 in here, and you have I5 and I6. So you have 6, total of 6 variables that we want to solve for. But we have 3 equations due to the loops that we did in here, the voltage, Kirchhoff voltage law. And now also we have a relationship between the currents. So we know that, for example, I6 is equal to I1 plus I2. Right there, it splits. This is I6 here. And splits into 2 I1. And we can do this at each node right here. And at each node. So we come up with these equations here. So this is just the, yeah, 4 more equations. Now, just to look at this, these are 4 equations plus 3 equations in there, but we gotta be careful in there because these equations, if we're gonna put all of these in, again, these are the values: R1, R2, R3, R4, and R5. So we're given this one, and we're given also the voltage V, which is 100 volts. So we are going to use these equations to come up with a we want to find I, actually, that's what we want to do. So let's start with, I'm going to write a script for this. So one thing that, if you look at this, you have 7 equations, right? This is 4 plus 3, so 7 equations, and you have 6 in now. So this is a little bit overdetermined in a way, because the number of equations is really higher than the number of elements. So in this case, still the left division will work, but we want to just be a little bit careful with this, because if you notice here that I6 appears in 2 equations in there, and I mean, we can definitely use equation 1, 2, 3, 5, and what is that here? 5, and also equation 6 to solve for these 5 variables from I1 to I5. And then as far as I6, we can use either of these equations. Remember, if you find I1, I2, I3, or I4, and I5, you can use this equation, for example, find I6. And same is true, you can use this equation to find I6. So we're going to work on these 2 plus this 3 up in there. Is that here? Plus 3 here. So we get 5 equations, 5 unknowns. So we'll solve for the currents I1 to I5, and then we have 2 equations to come up with the value of I6. So that's exactly what we want to do. Just throw this one here, and I'm going to open a new script file, and all right. So let's start with defining R. R equal. I'm going to start with the first one here. So R, let me define R first, because he's given us that. So it is, we're all going to open the resistance is 1 and 5. It's an array, and 10, and also 5 times 1000, because it is kilo ohms. I'm just gonna do this. So this is an array. So we have R1 is equal 1, R2 equal 5, R2 equal 3. This is exactly what he's given us here. R1 equal 1, R2 5, and also is given us V. So let's also do V here. Little z is equal to 100. And just suppress that. So we have defined the resistance and we defined the voltage. So now let's just do A, and let's start with the first 3, those 3 equation here. So A, cool. So it is, I'm gonna do from I1, I2, I3, and I5, and the constant will take them to the right-hand side. So in this case, I1 will be 0, right? I2 will be minus R2. So minus R2, right? R3 is 0. R4 is minus R4, right? Okay. And then you have R5 is, in this case, I5, it is also 0. So what we want to do is also put 0, and that will give you the first equation. Even though that you don't have I1 and you don't have I3 and you don't have I5, you just have to put zeros in there. So the second equation, we have a I1, so R1, I2 also minus R2, and also R3, and we have also R4 0 and R5, I5 is 0. That will be the second equation. Okay. I made a mistake here because I have to put here a sorry, you have to be parentheses because this is, I'm going to pull it from the array that I formed in there. So you have to put a parenthesis in there to put that index element. Okay. So every single time you call any element in this array, you know what? Let me here. Okay. All right. So again, this is the first equation, and I'm just going to do this one here. So now this is the second row. It's going back to this one here. You'll have problem. I do not want to. All right, now the third row will. It doesn't have any I1, so we have 0. It doesn't have any I2. It has I3, which is minus R3, and also it has R4, I4, so minus R4, and also the lastly is R, and so that is equation 3. So I'm done with this. I'm gonna just grab these equations here now, and remember I'm gonna leave I6 out of it, so I'm just gonna do these two here. Okay, so let me do this 3 because I want to continue, and so we'll come back to the fourth equation, and in this case you're gonna have 1 because there's an I1. Actually, there is no I1, so it's gonna be 0. I am actually not looking for these two, looking for these two. Okay, the second and the third equation. So I1 is 0, I2 is 1, right? And I3 is 1, I4 is minus 1, and I5 is 0. So that will give you this equation, fourth equation, and then the last equation will be 1, I1, 0 for I2, minus 1 for I3, and 0 for I4, and minus 1 for I5. So here we go. We're done with all these 5 equations and 5 unknowns. Okay, so this is the first equation, right? Second equation here, third equation, and this is fourth equation, and this is fifth equation. I'm just gonna do separate the. Now we're just gonna do the B, and B is really straightforward because you only have one value, the rest are all zeros. So if you look at the first equation, that is the only one we're gonna bring back. This one here, we're gonna bring it back in here. So that was gonna be minus V in here for the first equation, minus V, and it's let me make sure 0, 0, 0, 0, and also 0. So, and then I'm going to close that, just separate that. Okay, so minus p 0, 0, 0, 0. That would be AB, and then so now we want to calculate the current. The current would be equal to what is that? Is equal to I'm going to do the left division, A, B divided by A, left division. And let me save that. Just do the editor here, save as. I'm just do this one. Example. Eight or save, and just run this one here, and see what I get in here. So that is what we get. Let me maximize this one here. So if you look at in this one, it will have these currents. Somehow I get different answer. Let me just make sure that my see if I put everything the correct way. So 1, 5, 2, 10. Okay, here we go. This is 5 in here. So that is 5. And let me rerun this and see what we get. Yeah, that looks much better. So yeah, that's it. Current 1, current 2, current 3, current 4, current 5. Okay, so these are the currents. Now, as far as I6, if you really want to find I6, you can just do something that what you're going to do is just I6 will be equal to one of these equations, I4 plus I5, and you can get, so if you just add these two here, it will give you I6. Okay, so use one of these equations and you will get the value of I6. So this is like, in a way, it's overdetermined problem. So you have more equations than and knowledge. You just have to be careful when you do this. Actually, the way you want to use it, you can calculate I6 and verify it with one equation. And I actually calculate it in one equation and verify it in this the second equation to make sure what you're doing is right. Okay, so very good example, good application for circuits, and it shows you the power of using MATLAB to calculate these types of linear algebraic equation. So let's move to this problem here. Let me enlarge this one here. All right, so what we have, the concept of thermal resistance described in problem 8 can be used to find the temperature distribution in the flat square flat shown. I'll talk about the concept in a minute. You know, for those of you who took heat transfer, uh, heat transfer, we call that the thermal circuits, is very similar to the electrical circuits, the way it works. So the heat transfer works exactly like current, and the voltage and the temperature works like a voltage. So pretty much the same way we just solve those loops inside the circuits. You can do the same thing when it comes to heat transfer. So, so nothing to it. I'm very sure most of you have already taken circuits, electric circuits, so it'll be very similar to that if you haven't taken the heat transfer. So let's continue reading in here. So we said that this is the circuit. So if I can enlarge it a little bit. Again, so you have T1 in here, T2. Maybe I'll just get other glasses. This is, and yeah, T1, T2, T3, T4, and you have TA here at the boundary and TB in here. Okay, so so a couple of things in a circuit, in a heat thermal circuits, you can have a heat conduction, you can have a heat convection, and you can have a heat radiation, and you can have a heat source in a way. But all these resistance, or we call this the heat resistance, we don't really care so much about the value of R, this R value, because it will be given if their conduction. In this case, if you look at this plate or this shape in there, it is divided into multiple 4 quadrants, and each quadrant has its own temperature. It looks like there is a conduction inside these 4 plates or 4 quadrants, and it looks like you have convection in here and convection in here. And if you look at here, this is mostly insulated in this. So probably have convection at A, convection at B, and the rest is insulated, which means when you have insulated, that means there's no heat. Q is 0 coming in here and there. And the rest will be conduction. So this is how we're going to do. So we have 4 conduction, and this is 1 or 2 convection right there. So this plate, the edges are insulated so that no heat can escape, except at that point we'll just talk about TA and TB. So the temperature varies through the plate, so no single points can describe the plate's temperature. One way to estimate the temperature is to imagine that the plate consists of 4 subsquares to compute the temperature in each subsquare. Let R be the thermal resistance of the material between the centers of adjacent subsquares. Then we can think of the problem as a network of electrical resistors. That is exactly how we solve thermal resistors. We equate, like I said, in a way, we equate the voltage to temperature and the current to heat transfer. And of the figure, and let Qij be the heat flow rate between the points, again, whose temperature Ti and Tj. Ta and Tb remain constant for some time, then the heat energy stored in each subsquare is constant also, and the heat flow rates between each subsquare is constant. Under this condition, conservation of energy says that the heat flow into a subsquare equals to the heat flow out. So whatever heat's coming in is equal to the heat going out. Energy conservation and energy. Applying this principle to each subsquare gives the following. Q, again, A1, again, coming from this one, this point to will be equal Q12 plus Q13. So, and the way, if you look at the subsquare, so let's go back in here. So, so whatever coming in here is going to leave here, and it's going to leave in here. Okay, and same is true. If you do this subsquare, you have 1 heat coming in and 2 leaving. So same is true for if you do subsquare 2, you get this is coming and this is leaving, and same thing for if you do this one here, this is coming and this is leaving, and here both are coming and this one is leaving. Okay, so nothing to it, just have to keep track what the heat's coming in and the heat is flowing out. Now, you might have said, okay, why the heat is not coming in this way? It doesn't matter. If the heat is coming this way, it's going to leave this way. So it's going to be, the negative sign is going to be at the end wash out. So I'm assuming that the heat is coming this way and it is leaving this way, right? So we're doing this for each subquadrant, and we're going to come up with these equations here. So these are these equation 1, 2, 3, and 4. Okay, and what we want to do, since QA1, which is the heat coming in to the first quadrant, is equal to TI in this case TA minus TJ over R, right? And so we can actually rewrite these in there, and if you rearrange these again, like for example for QA1, you're going to write that as TA minus T1, right, divided by R, and in this case it would be R1 right there. Okay, or in this case I'm just going to find R can be cancelled, so that would be R, right? So this is 1 in here, and then you're going to do the same thing here, is equal to T1 minus T2 over R, and then the last one will be equal to plus T1 plus T1 minus T3 divided by R, so all will cancel. So in this case, you can rearrange this, you will come up with this equation. Okay, T1 will be equal 1/3 TA plus T2 plus T2, T3, and same thing here for the second equation, come up with this, and that will give you the third equation, and that will give you the fourth equation. And all I'm doing is just applying this. The heat will be equal to the change of temperature divided by the resistance. We're given TA and TB, and that's what we assume, because always the heat flows from high medium or hot medium to a low medium. So our assumption was right. We start at 150, and then we'll leave at 20. All right. So if you ever take a heat transfer, or if you've taken it so far, you will know that when we do the heat circuits, that's exactly what we do. We again do heat resistance through a convection process or conduction process or radiation process. And once we do that, we can do those energy equation across any point or any area within that heat. If it's a wall, if it is anything that you want, you can just apply the energy equation. Always the energy equation, you have whatever heat's coming into the system should be equal to the heat leaving the system. Now, assuming this is steady state heat transfer. Now, if you're using transient heat transfer, that will be a different story, and we'll talk that then you can't use this, use something else to do this. Because transient, now it's depending on time, it is not steady state, so equations will change, everything will change with time. So let's try to solve these equations and so we have four equations, and let's see what we can let's rearrange this, and we know TA, TB, so we want to find T1 and TB. So T1, T2, and T3. So if you rearrange these equations here, you can start with this one. The first equation, you're going to have 3 T1 minus T2 minus T3 is equal to TA. And the second equation will be T1 minus T2 plus T4 to 0. And the third equation, this one will become T1 T1 plus minus actually T3 plus T4 is equal to 0. And the fourth equation will become T2 plus T3 minus 3T4 and equal minus T. Okay. So as you can see, four equations, four unknowns. We can pick up A from there. So what is A in this case? Let me scroll in here. So, so we're done with this. So just this one and open a new. So with that, we'll do the A in here. Cool. So we have 3 minus 1 minus 1 0. That's the first row. Maybe even T4, there's no T4, you have to put 0 in there. First equation, second equation is 1 minus 2 0 and 1. And again, I do third equation 1 0 minus 2 and 1. And the fourth equation 1 and 0 because there is no T1, and you have 1 1 minus 3 1 0 1 1 minus 3 and 0. Okay, so for equation relate to 0 1 1 and minus 3. And I'm just going to close this one. So this is A. Again, this is the first equation. Second equation. Right? Third equation. And this is the fourth equation. So now we're ready to put B in there. So B is equal to open the bracket. So that 150 0 0, and then TB is actually minus 20 minus TB minus 20. And I'm gonna have that, and just gonna do X equal again left division. Okay. Right, so let's save this one here. Nine. Okay, so let's call this 0.9. Let's run this one here. So if you run it, you'll see that this is the temperature in the first sub-quadrant. This is for the second, third, and this is the fourth. Okay, and so these are T1, T2, T3, and T4. 4 equations, 4 unknowns. So we have unique solutions for this. So far we have done unique solutions problems for this. So we really want to do something a little bit more now, where we have undetermined problems or undetermined linear algebraic problems. So let's move to this problem. Right, so we're done with this. Let's read this problem here. Solve this equation: 7x plus 9y minus 9z equal 22, 3x plus 2y minus 4z equal 12, x plus 5y minus z equal minus 2. So we want to solve these equations and see what we get first, right? But just looking at this, we don't know if this, let's try to do it. Let's try to do it before, and we'll see what that will give us. So we're going to do the left division, and we'll see what that will give us. I'm going to just do this from the command window. So what do we have? We have, let's choose A equal, in this case, 7 equal 7, 9 minus 9, and then the second equation, 3, 2 minus 4, and 1, 5 minus 1. So that will be the A, and B in this case is equal 22, 12, and minus 2. Okay, so that's A and B. And if I were to let me do the left, the x, and let's say x is equal to A. I'm going to do the left there and see what we get. So here we go. We said that if you do this, you're going to come up with matrix is close to singular or badly scaled, so the result may be inaccurate. And it's given us x. So we're going to hang on to this, and we're going to investigate that, see why it's given us this for badly scaled. So it looks like there's something wrong with the rank. So let's see if rank, let's do rank A, and see what we have. Rank A is 2, and let's do rank A and B. So A, B, close, and see. Rank A and B is, in this case, is 2 and 2. So the rank A is equal to rank B. But if you notice here, the ranks are equal and less. They're equal, but they're less than the number of the variables. Remember, we have x and y and z, and when you have the rank is less than the number of variables, so you have actually, in this case, you have an infinite number of solutions for this. So how do we do this using ANSYS, using MATLAB? So again, the first thing, there's solutions, but there's definitely there's no unique solution for this. There is infinite solution, because even though the ranks of A is equal to rank AB, but R, which is the rank of A, is actually less than the number of variables. In this case, number of variables. M. M is number of equation, N is number of variables, and R is the rank of these equations. So how do you solve? We're going to use the RREF command to see how this will work. So I'm going to just do RREF, and gonna do AB, and see what that will give us. A. So this is what's going to happen. It's going to reduce. So let's do this. It's going to reduce our equations from 3 equations and 2 unknowns. Sorry, 3 equations, 3 unknowns, to 2 equations, 2 unknowns. So just notice what happened in here. Notice, look at the third equation that we get here, 0, 0, 0, 0. So we don't really have to worry about that. So now what we have in there, you have this is 0, and you have z, and you have y, and you have z. So if you notice, you can actually put an x as a function of z and a y as a function of z in this case. So in other words, if I want to rewrite this, let me rewrite this, what I get in here. So what I get in this, what does that mean here? So let me just copy that and put it in perspective here, because I really want to see what that means here. So let me paste that. Just put that one here. Oh, did not do it. So, all right, so I don't know where did it go. Let me open that. Copy. Go here. Let me copy this one here. So, all right. So that's what I got in here. So what I want to do, I want to explain what that means. So remember, again, this is x here, y, and this is z, and this is the constant. Okay? So the first row, you're going to get x is equal to minus 1.3846. Z is equal to 4.9231. So x is equal to 1.384 z plus 4.9231. That will be the first equation that I get from the RREF command. And the second equation here, we'll have y plus 0.076923 is equal to minus 1.3846. So y will be equal to minus 0.076923 z minus 1.3846. So that is equation 2. So you notice here that that's why we talked about infinite solutions. So for every value of z, you're going to have a value for new value of x for new value of y. So there's actually unlimited number of solutions for that. And this is exactly what we want. We want x as a function of z and y as a function of z, and we can change z, and we will get the corresponding value for x and y. So that is That is, when we talk about unlimited solution, we want to define what these are unlimited, what these unlimited solutions that we're talking about, and this is one way of doing this uh, by just specifying the functions or equation of x as a function of and y as a function of c. So I believe I'm just going to do one more problem, and yeah, maybe one more problem, and then I'll stop and see what we can. Yeah, let's do one more problem. And remember, when I was doing the lecture, we talked about that traffic light flow, and I'm going to get back to this one. So let's read this one here. Okay, so we have, so assuming that no vehicles, look at this, and maybe I can enlarge this one here. So assume that no vehicles stop within the network. A traffic engineer wants to know if the traffic flows F1 and F2 to F7 in vehicles per hour can be computed given the measured flows shown in the figure. If not, then determine how many more traffic sensors need to be installed to obtain the expressions of the other traffic flows in terms of the measured quantity. So remember, we're measuring these traffic here. And we're trying to find the traffic within F1, F2, F3, F4. Remember, there's, for example, F1 200 plus 100 is coming. That will be that node. And what's leaving is F1. So we're going to do actually the balance at each node in there to come up with equation. It's pretty similar to the circuits as a current. You can think about it as an electric current that's coming. So again, 200, for example, for node 1, 200 plus 100 coming, leaving is F1 and F3. For this node is 300 is coming, F1 is coming, F2 leaving, F4 is leaving. So you do that balance across all of this and see if this is sufficient for us. So if you do the balance, so let's do the balance. So if you, let me start with the first thing. We'll do this for the first one. Node 1, so we have 100 plus 200, and then it was 1 plus 2. And the second node, you're going to have 1 plus 300 is equal to F2 plus F4. Okay. Third node, F2 is coming, 5 is coming, and 2 is 100 and 4. Fourth node, F3, 6, leaving 100 plus 300. Okay, so we are here right now. And now 5 is F4 is coming, 7, 6, and also 200. And finally, the last node is 200 plus 400. 5. Okay, so if you think about this, we can rearrange this because we're trying to solve. We can rearrange those. Put the constant on the right and the or keep the constant on the right and move the for example, for the first one, for the first equation here, becomes f1 plus f3 is equal to 300. Okay, and for this one, the second one will be f1 minus f2 minus f4 is equal to 400, and so on. You can do the same thing. Rearrange those, and then start working on the matrix. So if you do this, you're going to come up with this matrix here. So what we're going to do, we're going to do AX equal B. So let me open this one here. And, yeah, I'm going to just work in this here. So let me put in there. And I'm going to put A in there. That will be the matrices. And first one will be 1, 0, and then 3 will be 1. And then you have 0, 0, 0. So remember, there's 1, 0, 1, 0, 0, 0. Actually, it's going to be so let me see if I 1, 0, 1, 0, 1, 2, 3, 4, 5, 6. So in this case, I have a 1, 2, 3, 4, 5, 6. Yeah, I have 6 by 7, right? Because it is 7 unknowns and 6 equations. No, let me write the script file on this. Script file. Script file is better. Here. So I'm doing a script file, but as you notice here, I'm just going back to this here. I have 1, 2, 3, 4, 5, 6 equations and 7 unknowns, because I have from F1 to F7, F1, F2, F3, F4, F5, F6, and F7. So I'm missing. So this is underdetermined problem. Maybe we want to do everything as a function of F7. So maybe we need to put another sensor at F7, and that will. But let's see what we get first. So this equation is going to be rearranged. So it's going to be, let's confirm A is equal to, the first row will be equal 1, 0, 1, and there's no F4, F5, F6, F7, so 0, 0, 0, 0. So 1, 0, 1, 0, 0, 0. So that is the first equation. Second equation is 1 minus 1, and then 0, 0, then minus 1, then 0, 0, 0. Okay, 1, 2, 3, 4, 5. Okay, and third equation. So the third equation will be 0, 1, 0, 0, 1, 0. Fourth equation becomes 0. Putting back those equations in there. All right. So you know what? Let me do this in here. Probably fit one more. All right. So 1, 2, 3. The fourth equation will be 0. 0, 0, because there is no F1 and there is no SF2. 0, 0. You have 1, 0, 0, 1, 0. So that will give you the fourth 1, 2, 3, 4, 5, 6, and then continue the next line. So that is the fourth. The fifth equation will be 0, 0, 0, 1, 0, minus 1, and 1. Then the last equation will be 0, 0, 0, 0, 1, 0, and 1. And I'm going to close that, and that will give you the A matrix, the B matrix. So B is equal 300 for the first one, and then you have minus 300, second one, 600, 400, 200. So that is, so if you look at this, I mean, we know that there's 6 equations and 4 nodes. So, you know, let me just save this. Let me just save this one here. You know what? Let me do this. Let me do, I'm going to try to do the left division. So x is equal to A B. Okay. And let me save that and see what we get, because that's what you want to do. But, you know, just looking at this, you know that you have 7 unknowns and 6. So this is really underdetermined. So we need to get more data to be able to solve for these. So let's see what we got here. So this is 8. And let me run this and let's see what we get. So what we got in here, it says here, the rank deficient, rank 5. Let's read that. Warning, rank deficient, and it did solve that. Oh, I don't know what this one here. Let me just read on this. All right, let me rerun this one here and see what I get. I want to read that for you. So, really important to understand. So rank deficient, rank 5 equal 5. and then it gives me a solution in here. And so remember the rank. Let's solve rank A. Something is okay. It's taking that A. All right, I did something here. Let's redo this. Let me put this. I write it in the script. So when I do this one here, it's giving me this. So what I want to do, I want to go and solve for rank A, right? And rank of AB. A, right? And I'm going to rewrite again and see what I get. So why is giving me right? Well, I'm treating it like I'm doing a command, so I'm just going to put rank of A is equal to rank of A, and rank of AB is equal to rank. I don't know why I'm doing this in a. So rank AB. Just gonna do this one here. Rank of A, rank of AB equal to rank of A. I'm used to working the command. So let me do that. See what we get here. So run it. So here we get rank of A is equal to rank of AB, which means that rank of A is equal to rank of AB is equal to 5, right? But rank of 5, we have 7 unknowns, F1 to F7. So we're lacking 2 unknowns, so not just 1. So how do we solve this problem? We're going to use the RREF command, because this is really underdetermined. RREF, and I'm going to just do A, B. RREF. Okay, yeah, I'm gonna actually see here and rerun it here. And I'm gonna actually do this, maximize, and read what's going on in this. Now, very important information we have in there. Now, what I want to do, if you look at this, just looking at the rank there, we have rank 5, and we have 7. So we know that we're probably going to need 2 unknowns needs to be redefined, not just 1. Like I said, 7 comparing to 5. But so how do we solve this problem? In this case, you can rewrite, because now you have F6. Let's put these equations, see what we have in there. So the first equation, you know what, let me copy these and see exactly. Let me copy this here and let's work on this on the Word file. So I'm gonna hold this and see exactly what we get in here. So let me just do this one here. And I'm going to write these equations and see exactly what I mean by that. Because, so this is column 1 through 5. But remember, we have now the 6 equation, but the last one has vanished. We have zeros in all columns. If you look at the last equation. So this is the first equation. Second equation, third, fourth, fifth. And look at the 6th equation, all zeros to here. Okay. So let's talk about the first equation. So the first equation, we have only f1 and minus f6 minus 100. So it is minus f6 equal 100. Okay. Second equation will give you f1, f2 is minus f7 equal to 0. Third equation is f3 f3 plus f6 is equal to 400, and we have f4, fourth one, is equal to f minus f6 minus plus f7, sorry, is equal to 200, and then f5 plus f7 is equal to 600. Okay, so let's do this one here. So the first one, f1 is equal to f6 plus 100. That is the first equation. f2 is equal to f7, and f3 is equal to 400 minus f6, and f4 is equal to f6 minus f7 plus 200, and the last one will be f5 is equal to 600 minus f7. So here we go. We have f1, f2, f3, f4, f5 as a function of f6 and f7. So in order for us to be able to find f1 through f5, you need to really specify f6 and f7. So sensors on these streets, f6 and f7, needs to be installed. So this way we can be able to calculate the rest. So go back to the schematic, and this is exactly what we did. Since the rank is less, the rank value for A and B, and rank of A is less than the number of variables, what we did, we used the RREF command to reduce the number of variables as a function, to reduce the number of equations actually, and put some of these variables as a function or as a function of other variables. And in this case, we know that because we have rank is 5, number of variables 7, we know that we're lacking 2 more dependent or independent variables that we need to define. So these dependent variables from f1 to f5 can be solved for. So if we go back to the schematic, so what we want to do here, we go and if we put a sensor here and put a sensor in here, f6 and f7, we'll be able to calculate these traffic in here, those 5 traffics. Otherwise, it won't happen. Okay. So that is the beauty of this RREF command that gives us a way to solve these, even though you have more variables than when you have more equations, you still can find out the relationship of some of these variables as a function of other variables that needs to be defined. So I guess that should do it for this chapter. We'll continue next time with the following chapter, and just want to remind you again about uh, the project. Please do not put it off. Start working on it. If you have any questions, you can always email me, and we can always discuss it in those hours, class and also office hours. Thank you very much, and we'll see you later in the next lecture. Thanks.